Interference and diffraction. This chapter will be challenging. However, if you take the right steps and you study early, you should do fine. And it's actually very interesting once you get over the fundamentals of the chapter. The streaks of colored light you see coming from a compact disc resemble the colors that appear when white light passes through a spectrum. However, the compact disc does not separate light by means of refraction. Instead, the light waves undergo interference. The chapter illustration. The color visible on the disk surfaces are characteristic of the light used in the photograph. Have students verify the ability of a compact disc to separate light into its particular spectrum by reflecting light from different sources off a compact disc's surface. For example, sunlight is separated into all of the visible colors, while most fluorescent lighting produces only a few colors. Chapter 15 overview. Interference identifies the conditions required for interference to occur and shows how to calculate and locate the bright and dark fringes in double slit interference. Diffraction describes how diffracted light waves interfere, shows how to calculate the position of fringes produced by diffraction grating, and discusses the resolving power of optical instruments. Lasers describe how a laser produces coherent light and explores applications of lasers. The superposition principle, when two mechanical waves pass through the same space at the same time, their displacements at each point add. When two waves with the same frequency and amplitude overlap, the resulting wave has the same frequency as the individual wave. If the waves are in phase, the resultant wave has twice their amplitude. If they are 180 degrees out of phase, the amplitudes cancel. Preconceptions about waves. Ask students what happens when two waves, A and B, travel towards each other on a string and meet at a point where A's displacement is 4 centimeters up and B's displacement is 3 centimeters up. The displacement at that point is 7 centimeters up. What if A is 4 centimeters up and B is 3 centimeters down? The displacement is 1 centimeter up. Chapter preview, 3 sections. First is interference, broken into 2 subsections, combining light waves and demonstrating interference. Diffraction is section 2, broken into the bending of light waves, diffraction gratings, and diffraction and instrument resolution. The third section, lasers, is broken into 2 subsections, lasers and coherence, and the second subsection, applications of lasers. What to expect. In this chapter, you will learn about interference of light. In interference, light waves combine to produce resultant waves that are either brighter or less bright than the component waves. Why it matters, devices called diffraction gratings use the principle of interference to separate light into its component wavelengths. Diffraction gratings are used in instruments called spectrometers, which are used to study the chemical composition and temperature of stars, as well as many other things. Section 1, interference, 3 objectives. Describe how light waves interfere with each other to produce bright and dark fringes. Identify the conditions required for interference to occur. And last, predict the location of interference fringes using the equation for double slit interference. Figure 1, light waves interfere to form bands of color on a soap bubbles surface. Study it carefully before proceeding. Combining light waves You have probably noticed the bands of colors that form on the surface of a soap bubble, as shown in Figure 1. Unlike the colors that appear when light passes through a refracting substance, these colors are the result of light waves combining with each other. Interference takes place only between waves with the same wavelength. To understand how light waves combine with each other, let us review how other kinds of waves combine. If two waves with identical wavelengths interact, they combine to form a resultant wave. Please look back at Figure 1 and see if that makes sense, what I just read. I usually try to put the figure before the text in which it is mentioned so that you can go back, put it on pause. This is a very important slide. Figure 2, two waves can interfere, A, constructively, or B, destructively. In interference, energy is not lost, but instead redistributed. This resulting wave has the same wavelength as the component waves, but according to the superposition principle, its displacement at any instant equals the sum of the displacements of the component waves. The resultant wave is the consequence of the interference between the two waves. Figure 2 can be used to describe pairs of mechanical waves or electromagnetic waves with the same wavelength. A light source that has a single wavelength is called monochromatic, which means single colored. In the case of constructive interference, the component waves combine to form a resultant wave with the same wavelength, but with an amplitude that is greater than the amplitude of either of the individual component waves. All right, this is a perfect time to go back and actually look at Figure 2. I will continue by looking at, very briefly, destructive interference. For light, the result of constructive interference is light that is brighter than the light from the contributing waves. In the case of destructive interference, the resultant amplitude is less than the amplitude of the larger component wave. For light, the resultant destructive interference is dimmer light or dark spots. Figure 3, A, the features of two waves in phase completely match, whereas B, they are opposite each other in waves that are 180 degrees out of phase. Waves must have a constant phase difference for interference to be observed. For two waves to produce a stable interference pattern, the phases of the individual waves must remain unchanged relative to one another. If the crests of one wave overlaps the crests of another, as in Figure 3a, the two have a phase difference of 0 degrees and are said to be in phase. If the crest of one wave overlaps the trough of the other wave, as in Figure 3b, the two waves have a phase difference of 180 degrees and are said to be out of phase. I will keep things running while you go back and check the nearest figure diagram. We are said to have coherence when the phase difference between two waves is constant and the waves do not shift relative to each other as time passes. Coherence, the correlation between the phases of two or more waves. Sources of such waves are said to be coherent. When two light bulbs are placed side by side, no interference is observed, even if the lights are the same color. The reason is that the light waves from one bulb are emitted independently of the light waves from the other bulb. Random changes occur in the light from one bulb do not necessarily occur in the light from the other bulb. I'm just going to let things run. You can look around. Thus, the phase difference between the light waves from the two bulbs is not constant. The light waves still interfere, but the conditions for the interference change with each phase change, and therefore no single interference pattern is observed. Light sources of this type are said to be incoherent. Let me read that again. Light sources of this type are said to be incoherent. Figure 4, an interference pattern consists of alternating light and dark fringes. Demonstrating interference. Interference in light waves from two sources can be demonstrated in the following way. Light from a single source is passed through a narrow slit and then through two narrow parallel slits. The slits serve as a pair of coherent light sources because the waves emerging from them come from the same source. Any random change in the light emitted by the source will occur in the two separate beams at the same time. If monochromatic light is used, the light from the two slits produce a series of bright and dark parallel bands or fringes on a distant viewing screen, as shown in Figure 4. When the light from the two slits arrives at the point on the viewing screen where constructive interference occurs, a bright fringe appears at that location. When Figure 5, when waves of white light from two coherent sources interfere, the pattern is indistinct because different colors interfere constructively and destructively at different positions. When the light from the two slits combines destructively at a point on the viewing screen, a dark fringe appears at that location. When a white light source is used to observe interference, the situation becomes more complicated. The reason is that white light includes waves of many wavelengths. An example of a white light interference pattern is shown in Figure 5. The interference pattern is stable or well defined at positions where there is constructive interference between light waves of the same wavelength. This explains the color bands on either side of the center band of white light. This effect also accounts for the bands of color seen on soap bubbles. Figure 6, very important to understand what we're reading. A, when both waves of light travel the same distance, length 1, they arrive at the screen in phase and interfere constructively. B, if the difference between the distances traveled by the light from each source equals a whole wavelength, lambda, the waves still interfere constructively. C, if the distances traveled by the light differ by half a wavelength, the waves interfere destructively. Figure 6 shows some of the ways that two coherent waves leaving the slits can combine at the viewing screen. When the waves arrive at the central point of the screen, as in Figure 6a, they have traveled equal distances. Thus, they arrive in phase and at the center of the screen. Constructive interference occurs and a bright fringe forms at the location. When the two light waves combine at a specific point off-center of the screen, as in Figure 6b, the waves from the more distant slit must travel one wavelength farther than the wavelength from the nearer slit because the second wave has traveled exactly one wavelength farther than the first wave. The two waves are in phase when they combine at the screen. A little confusing, but not bad. Constructive interference, therefore, occurs and a second bright fringe appears on the screen. If the waves meet midway between the locations of the two bright fringes, as in figure 6c, the first wave travels half a wavelength farther than the second wave. If, in this case, the trough of the first wave overlaps the crest of the second wave, giving rise to destructive interference. Consequently, a dark fringe appears on the viewing screen between the bright fringes. Let's look at another figure, figure 7. The path difference for two light waves equals d sine theta. In order to emphasize the path difference, the figure is not drawn to scale. That's going to be the hard part about this chapter, is we're going to be calculating very, very small angles, and the pictures are going to be difficult to illustrate. Figure 7, visual strategy. Point out that lines L1 and L2 should intersect for interference to occur. They are represented as parallel only as an approximation, so that the path differences can be found mathematically. Question: if d equals 0.5 millimeters and theta equals 0.30 degrees, how large is the path difference? Again, you see that we're going to be using very small angles, small distances, small lengths. The answer is d sine theta equals 2060 nanometers, or 5 wavelengths of the light. We'll make that, it'll make a little more sense once we start doing problems. Predicting the location of interference fringes. Consider two narrow slits that are separated by a distance d, as shown in figure 7, and through which two coherent monochromatic light waves, lambda 1 and lambda 2, pass and are projected onto a screen. If the difference from the slits to the viewing screen is very large compared with the distance between the slits, then lambda 1 and lambda 2 are nearly parallel. As a result of this approximation, lambda 1 and lambda 2 make the same angle theta with the horizontal dotted lines that are perpendicular to the slits. The angle theta also indicates the position at which the waves combine with respect to the central point of the viewing screen. My recommendation here for this slide is to put things on pause, rewind, and watch it again, and look at some of the figures as you read it again. The difference in distance traveled by the two waves is called their path difference. Path difference, the difference in the distance traveled by two beams when they are scattered in the same direction from different points. Study the light triangle shown in figure 7, and note that the path difference between the two waves is equal to d sine theta. Note carefully that the value for the path difference varies with angle theta, and that each value of theta defines a specific position on the screen. The value of the path difference determines whether the two waves are in or out of phase when they arrive at the viewing screen. If the path difference is either 0 or some whole number multiple of the wavelength, the two waves are in phase, and constructive interference results. The condition for bright fringes, constructive interference, is given by equation for constructive interference, d sine theta equals plus or minus m lambda, where m equals 0, 1, 2, 3, etc. The path difference between two waves equals an integer multiple of the wavelength. In this equation, m is the ordered number. Order number, the number assigned to interference fringes with respect to the central bright fringe. Let me read that again without reading the definition. In this equation, m is the order number of the fringe. The central bright fringe at theta equals 0, m equals 0, is called the 0th order maximum or central maximum. The first maximum on either side of the central maximum, which occurs at m equals 1, is called the first order maximum, and so forth. Similarly, when the path difference is an odd multiple of 1/2 lambda, the two waves arriving at the screen are 180 degrees out of phase, giving rise to destructive interference. The condition for dark fringes or destructive interference is given by the following equation. The equation for destructive interference, d sine theta equals plus or minus m plus 1/2 that quantity times theta times m, which equals an integer, 1, 2, 3, etc. The path difference between two waves equals an odd number of half wavelengths. If m equals 0 in this equation, the path difference is plus or minus 1/2 lambda, which is the condition required for the first dark fringe on either side of the bright central maximum. Likewise, if m equals 1, the path difference is plus minus 3/2 lambda, which is the condition for the second dark fringe on each side of the central maximum, and so forth. The higher order, m equals 1, 2, etc., maxima appear on either side of the central maximum, m equals 0. And these are very, very, very small angles, by the way, so it's difficult to make a drawing of them. Figure 8, visual strategy, have students notice that the dark and bright fringes form a symmetrical pattern. Look back at that figure and see if that's true. How many 0th order bright lines are there? How many dark ones? Look back, see what you see. And the answer is 1 and then 2. There's actually two questions there. 1 0th order and 2 dark ones. A representation of the interference pattern formed by double-slit interference is shown in Figure 8. The numbers indicate the two maxima, plural of maximum, that form on either side of the central 0th order maximum. The darkest areas indicate the position of the dark fringes, or minima, plural of minimum, that also appear in the pattern. Because the separation between interference fringes varies for light of different wavelengths, double-slit interference provides a method of measuring the wavelength of light. In fact, this technique was used to make the first measurement of the wavelength of light. Interference sample problem A, the distance between the two slits is 0.030 millimeters. The second order bright fringe, m equals 2, is measured on the viewing screen at an angle of 2.15 degrees from the central maxima. Determine the wavelength of the light. All right, so we want to gather what we're given, and we're going to write it down. You want to convert the distance to meters. You have m equals 2, and you have the angle, and you're looking for the wavelength. So now we're ready. Let's look, though, first at a diagram of what we're actually working with. Now, again, the diagram is not going to be drawn perfectly from scale, but that's the diagram. It says diagram not to scale. Second order bright fringe, m equals 2, 0th order bright fringe, m equals 0. So now we've got to find the angle of the wavelength. Choose an equation or situation. use the equation for constructive interference. Now, we have the angle and we're looking for the wavelength. So here's the equation, the simplified form. We're going to solve for wavelength, and we're going to say substitute in the values into the equation and solve. And we'll just run it right out. There's the values. I'm going to use this equation, and I'm going to plug it in thusly and calculate it like that. So the wavelength is 5.7 times 10 to the negative 5 meters. This wavelength of light is in the visible spectrum. The wavelength corresponds to light of a yellow-green color. Yellow-green is the dominant light from the sun, by the way. There's the scale again, just to show you that, and then show you one more thing before we move on to some problems, and that is the wavelength answer. Okay, so it's 5.7 times 10 to the negative fifth, and it is a wavelength which corresponds to light of yellow-green color. Right, now, problem set A, interference. A double slit interference experiment is performed with blue-green light from an argon gas laser. Lasers will be discussed further in section 3. The separation between the slits is 0.5 millimeters, and the first order maximum of the interference pattern is at an angle of 0.059. From the center of the pattern, what is the wavelength of argon laser light? Okay, so that's the problem. And now what do we want to do? Well, we want to put down what we have. We want to change the distance to meters. And we have the angle, and we have m equals 1. So you're going to plug in the various values, and you're going to calculate 5.1 times 10 to the negative 7th meters, or 510 nanometers. And light falls on a double slit with slit separation of 2.02 times 10 to the 6th meters. That's kind of like micrometers. And the first bright fringe is seen at an angle of 16.5 degrees relative to the central maximum. Find the wavelength of the light. So here is what's given, already converted to meters, and we're going to use the equation to solve for lambda, and that's the plug-in, and that's the answer, 574 nanometers. A pair of narrow parallel slits separated by a distance of 0.250 millimeters is illuminated by the green component from a mercury vapor lamp. Lambda equals 546.1 nanometers. Calculate the angle from the central maximum to the central bright fringe on either side of the central maximum. There's the information, and there's the equation. You're going to plug into the equation, and you're going to solve 0.125 degrees. Using the data from item 2, determine the angle between the central maximum and the second dark fringe in the interference pattern. So what are you going to do different? What are we going to do different relative to the problem that we did in item 2? Okay, so here's what's given, and then we'll put the equation down, and then we're going to plug in, and there you have it, 25.2 degrees. Section review: what is the necessary condition for a path length difference between two waves that interfere constructively? How about destructively? A difference of an integral number of wavelengths, a difference of an odd integral number of half wavelengths. So that's actually two questions. The first part is constructive, and the second is destructive. If white light is used instead of monochromatic light to demonstrate interference, how does the interference pattern change? The plot thickens, as they say, when the plot is about to thicken. It becomes blurred, and the bright fringes are made up of narrow, colored bands. Mystery solved. Whoa, I feel so much better. Okay, number 3. If the distance between two slits is 0.050, find the angle between the first order and second order bright fringes for yellow light with a wavelength of 605 nanometers. So that's 605 times 10 to the negative ninth. Okay, let's do it. Here's what we have. Things are converted to meters. M equals 1. And I have my lambda converted to meters. And there it is. And it's going to be 0.63 degrees. And now for m equals 2, again, you want to list the new equation. Simple difference is that the m is going to be 2, so I put a subscript m equals 2. Same data except for the 2. So this will be 1.62 degrees. So the change in theta will be theta 2 minus theta 1, which will be 0.63. Interpreting graphs. Two radio antennas simultaneously transmit identical signals with a wavelength of 3.35 meters, as shown in Figure 9. A radio several miles away and a car traveling parallel to the straight line between the antennas receives the signals. If the second maximum is located at an angle of 1.28 degrees north of the central maximum for the interfering signals, what is the distance d between the two antennas? That's a little bit more interesting. All right, let's look at Figure 9. There's Figure 9. Notice it's difficult to draw at the scale, but fair enough. That's the wavelength, theta, and m. So you're going to solve for d, rearrange the equation, plug in, and solve. And you have d equals 300 meters. Section 2, diffraction. Describe how light waves bend around obstacles and produce bright and dark fringes. Calculate the positions of fringes for a diffraction grating. Describe how diffraction determines an optical instrument's ability to resolve images. Figure 10, a property of all waves is that they bend or diffract around objects. The bending of light waves. If you stand near the corner of a building, you can hear someone who is talking around the corner, but you can't see the person. The reason is that sound waves are able to bend around the corner. In a similar fashion, water waves bend around obstacles, such as the barrier shown in Figure 10. Light waves can also bend around obstacles, but because of their short wavelengths, the amount they bend is too small to be easily observed. If light traveled only in straight lines, you would not be able to observe an interference plan in the double slit demonstration. Instead, you would see two thin strips of light where each slit and the source were lined up perfectly. The rest of the screen would be completely dark. The edges of the slits would appear on the screen as sharply defined shadows, but this does not happen. Some of the light bends to the right and to the left as it passes through each slit. The bending of light as it passes through each of the two slits can be understood using Huygens' principle, which states that any point on a wave front can be treated as a point source of waves. because each slit serves as a point source of light, the waves spread out from the slits. The result is that light deviates from a straight line path and enters the region that would otherwise be shadowed. This divergence of light from its initial direction of travel is called diffraction. Diffraction, a change in the direction of a wave when the wave encounters an obstacle, an opening, or an edge. In general, diffraction occurs when waves pass through small openings around obstacles or by sharp edges. When a wide slit, 1 millimeter or more, is placed between a distant light source and a screen, the light produces a bright rectangle with clearly marked edges on the screen. Figure 11, diffraction becomes more evident as the width of the slit is narrowed. Note the wavelength of this light is 510 nanometers. Study this figure carefully. But if the slit is gradually narrowed, the light eventually begins to spread out and produce a diffraction pattern, such as that shown in Figure 11. Like the interference fringes in the double slit demonstration, this pattern of light and dark bands arises from the combination of light waves. Wavelets in a wave front interfere with each other. Diffraction patterns resemble interference patterns because they also result from constructive and destructive interference. In the case of interference, it is assumed that the slits behave as point sources of light. For diffraction, the actual width of a single slit is considered. According to Huygens' principle, each portion of a slit acts as a source of waves. A, by treating the light coming through the slit as a line of infinitely thin sources along the slit's width, one can determine, B, the conditions at which destructive interference occurs between the waves from the upper half of the slit and the waves from the lower half. Hence, light from one portion of the slit can interfere with light from another portion. The resultant intensity of the diffracted light of the screen depends on the angle theta through which the light is diffracted. To understand the single slit diffraction pattern, consider Figure 12a, which shows an incoming plane wave passing through a slit of width A. Each point, or more accurately, each infinitely thin slit within the wide slit is a source of Huygens wavelets. The figure is simplified by showing only 5 among this infinite number of sources. As with double slit interference, the viewing screen is assumed to be so far from the slit that the rays emerging from the slit are nearly parallel. At the viewing screen's midpoint, all rays from the slit travel the same distance, so a bright fringe appears. The wavelets from the 5 sources can also interfere destructively when they arrive at the screen, as shown in Figure 12b. When the extra distance traveled by the wave originating at point 3 is half a wavelength longer than the wave from point 1, these two waves interfere destructively at the screen. At this same time, the wave from point 5, travels half a wavelength farther than the wave from point 3, so these waves also interfere destructively. At this stage, I would like you to put things on pause and go back and check to see if it makes sense relative to what we read. Look at the figure. With all pairs of points interfering destructively, this point on the screen is dark. For angles other than those at which destructive interference completely occurs, some of the light waves remain uncancelled. At these angles, light appears on the screen as part of a bright band. The brightest band appears in the pattern center, while the bands to either side are much dimmer. The next figure will help you. Figure 13, in a diffraction pattern, the central maximum is twice as wide as the secondary maxima. Study this very carefully. Look at the central maxima, look how bright and crisp it is. Light diffracted by an obstacle also produces a pattern. The diffraction pattern that results from monochromatic light passing through a single slit consists of a broad, intense central band, the central maximum, flanked by a series of narrower, less intense secondary bands called secondary maxima, and a series of dark bands, or minima. An example of such a pattern is shown in Figure 13. The points at which maximum constructive interference occurs lie approximately halfway between the dark fringes. Note that the central bright fringe is quite a bit brighter and about twice as wide as the next brightest maximum. Go back and look at Figure 13 and make sure what is written here makes sense there. Figure 14, a diffraction pattern forms in the penny's shadow when light is diffracted at the penny's edge. Note the bright spot that is formed at the center of the shadow. Looks like a kind of like a fingerprint. Very cool. Diffraction occurs around the edges of all objects. Figure 14 shows the diffraction pattern that appears in the shadow of a penny. The pattern consists of the shadow with a bright spot at the center and a series of bright and dark bands of light that continue to the shadow's edge. The penny is large compared with the wavelength of the light, and a magnifying glass is required to observe the pattern. Diffraction gratings. You have probably noticed that if white light is incident on a compact disc, streaks of color are visible. These streaks appear because the digital information, alternating pits and smooth reflecting surfaces on the disc, forms close spaced rows. These rows of data do not reflect nearly as much light as the thin portion of the disc that separates them. These areas consist entirely of reflecting material, so light reflected from them undergoes constructive interference in certain directions. Figure 15, compact discs disperse light into its component colors in a manner similar to that of a diffraction grating. Same thing with DVDs, I would imagine. This constructive interference depends on the direction of incoming light, the orientation of the disc, and the light's wavelength. Each wavelength of light can be seen at a particular angle with respect to the disc's surface, causing you to see a rainbow, Roy G. Biv, of color as shown in Figure 15. This phenomena has been put to practical use in a device called a diffraction grating. A diffraction grating, which can be constructed to either transmit or reflect light, uses diffraction and interference to disperse light into its component colors with an effect similar to that of a glass prism. A transmission grating consists of many equally spaced parallel slits. Gratings are made by ruling equally spaced lines on a piece of glass using a diamond cutting point driven by an elaborate machine called a ruling engine. Replicas are then made by pouring liquid plastic on the grating and then peeling it off once it has set. This plastic grating is then fastened to a piece of glass or plastic for support. Now you want to look back at all of the figures in this section. Things will make sense, especially when we do the next slide, which is also a figure. Figure 16, light of a single wavelength passes through each of the slits of a diffraction grating to constructively interfere at a particular angle theta. To constructively interfere at a particular angle theta. Figure 16 shows a schematic diagram of a section of a diffraction grating. A monochromatic plane wave is incoming from the left, normal to the plane of the grating. The waves that emerge nearly parallel from the grating are brought together at a point P on the screen by the lens. The intensity of the pattern on the screen is the result of the combined effects of interference and diffraction. Each slit produces diffraction, and the diffracted beams in turn interfere with one another to produce the pattern. For some arbitrary angle theta measured from the original direction of travel of the waves must travel different path lengths before reaching point P on the screen. Note that the path differences between waves from any two adjacent slits is d sine theta. Conceptual challenge, there are two. First, spiked stars. Photographs of stars always show spikes extending from the stars. Given that the aperture of a camera's rectangular shutter has straight edges, explain how diffraction accounts for the spikes. Radio diffraction. Visible light waves are not observed, diffracting around buildings or other obstacles. However, radio waves can be detected around buildings or mountains even when the transmitter is not visible. Explain why diffraction is more evident for radio waves than for visible light. Aha. The plot's about to thicken, as they say when the plot is about to thicken. Spiked stars. The edges of the camera shutter diffract light, causing secondary maxima to appear on the side of the star's image. These maxima give the appearance of light spikes around the star. And radio diffraction, the wavelengths of radio waves is much longer than that of visible light. Very curious. If this path difference equals one wavelength or some integral multiple of a wavelength, waves from all slits will be in phase at P, and a bright light will be observed. The condition for bright lines formation at angle theta is therefore given by the equation for constructive interference, or d sine theta equals plus or minus m lambda, where m is a integer. This equation can be used to calculate the wavelengths of light if you know the grating spacing and the angle of deviation. The integer m is the order number for the bright lines of a given wavelength. If the incident radiation contains several wavelengths, each wavelength deviates by a specific angle, which can be determined from the equation. Figure 17, light is dispersed by a diffraction grating. The angle of deviation for the first order maxima is smaller for blue light than for yellow light. Fascinating. Absolutely fascinating. Note in figure 17 that all wavelengths combine at theta equals 0, which corresponds to m equals 0. This is the 0th order maximum. The first order maximum corresponds to m equals 1, is observed at an angle that satisfies the relationship sine theta equals lambda over d. The second order maximum corresponds to m equals 2, is observed at an angle where sine theta equals 2 lambda over d. The sharpness of the principal maxima and the broad range of the dark areas depend on the number of lines in a grating. The number of lines per unit length in a grating is the inverse of the line separation d. Figure 18. Light of a single wavelength passes through each of the slits of a diffraction grating to constructively interfere at a particular angle, theta. This is a fairly important figure. Study this very carefully. Those angles are smaller than it appears in the figure. For example, a grating ruled with 5,000 lines per centimeter has a slit spacing d equal to the inverse of this number. Hence, d equals 1/5000th centimeter, which equals 2 times 10 to the negative 4 centimeters. The greater the number of lines per unit length in a grating, the less separation between the slits and the farther spread apart the individual wavelengths of light are. Diffraction gratings are frequently used in devices called spectrometers, which separate the light from a source into its monochromatic components. A diagram of the basic components of a spectrometer is shown in figure 18. The light is to be analyzed, passes through a slit and is formed into a parallel beam by a lens. The light then passes through the grating. Look back at the figure. Always refer back to the figures. Figure 19 is something which may be familiar from chemistry. The light from mercury vapor is passed through a diffraction grating, producing the spectrum shown. Roy G. Biv, but backwards. The diffracted light leaves the grating at angles that satisfy the diffraction grating equation. A telescope with a calibrated scale is used to observe the first order maxima and to measure the angles at which they appear. From these measurements, the wavelengths of light can be determined and the chemical composition of the light source can be identified. An example of a spectrum produced by a spectrometer is shown in figure 19. Spectrometers are used extensively in astronomy to study the chemical composition and temperature of stars, interstellar gas clouds, and galaxies. Again, always look back, take your time. Don't just let this read through like it's some novel. Keep stopping, pausing, and looking back. Let's do sample problem B. Monochromatic light from a helium neon laser, lambda equals 632.8 nanometers, shines at a right angle to the surface of a diffraction grating that contains 150,500 lines per meter. Find the angle at which one would observe the first order and second order maxima. Well, let's write down what we have. We have the lambda corrected for meters. We have m equals 1 and 2, and we have the number of lines per meter. We know that the unknowns are angle 1 and angle 2. Let's look at a diagram to help us further understand the model we're working with. There are the angles. Now, don't forget that these are small angles. It may appear large, but they're actually small. Okay, we want to choose an equation, and it's going to be for the first order maximum where m equals 1, and that's the data. Notice that everything is in meters. There's the equation for theta 1, and theta 1 equals Everything's plugged in, so theta 1 equals 5.465 degrees. Now let's do m equals 2, and there again is the data. Now the only difference is going to be that we'll put in a 2 instead of a 1, and that will give us 10.98 degrees. The second order maximum is spread slightly more than twice as far from the center as the first order maximum. This diffraction grating does not have high dispersion, and it can produce spherical lines up to the 10th order maximum, where sine theta equals 0.9524. 1. A diffraction grating with 5,000 lines per centimeter is used to examine the sodium spectrum. Calculate the angular separation of the two closely spaced yellow lines of sodium, 588.995 nanometers and 589.592 nanometers in each of the first three orders. Here are the givens. Now remember, you have to do lambda 1 and lambda 2 for each of the three orders. So watch the subscripts, and that will help you figure things out. This is lambda for lambda 1, lambda 2. Okay. So we're going to do the angular separation for each lambda 1 and lambda 2. Notice the lambda 1 and lambda 2 are converted to meters. All right, this is the m equals 1 for lambda 1. That's lambda 1, 17.13. And then notice the change. I put in lambda 2, and that's going to be 17.15. And now we'll calculate the difference for the m equals 1, now that we have the lambda 2 and lambda 1. And the difference is 0.02. Now this is for m equals 2. All right, this is lambda 1 for m equals 2, 36.09. And then we'll plug in lambda 2 and get the theta is 36.13. And then we'll calculate the difference for m equals 2 for lambda 2 and lambda 1 for the angles, and it's going to be about 0.04. Now let's do m equals 3. Here is lambda 1, 62.07, lambda 2, 62.18. Again, you just have to be very organized and neat, and things will be fairly clear. All right, this is going to be lambda 2 for m equals 3, and the difference is going to be 0.11 degrees. So you can see things are fairly small. All right, that's m1, m equals 1, m equals 2, m equals 3, and we'll compare the differences. So you're going to see a pattern here, 0.02, 0.04, and 0.11. That's it. A diffraction grating of 4,525 lines per centimeter is illuminated by direct sunlight. The first order solar spectrum is spread out on a white screen hanging on a wall opposite the grating. At what angle does the first order maximum for blue light with a wavelength of 422 nanometers appear? At what angle? Now notice you have to make sure things are correctly lined up. This is going to be lines per centimeter for m equals 1. And you want to change the wavelength for the blue and the red. to meters and change the lines per centimeter to lines per meter. And that was A, and now B. And this is for red. And it's 17.2. And here is a summary of the problem. Theta blue is 11 degrees, and theta red is 17.2 degrees. A grating with 1,555 lines per centimeter, make sure you correct that to meters, is illuminated by light of wavelength 568 nanometers. What is the highest order number that can be observed with this grating? Hint, remember that the sine theta can never be greater than 1 for a diffraction grating. All right, so that's per meter. That's theta. And there is the givens. Here's the equation. And that's m equals 11, m equals 12. Plug in the values. 75.1 for m equals 11. And infinity for m equals 12. Therefore, 11 is the highest order number that can be achieved. Number 4, repeat item 3 for a diffraction grating with 15,550 lines per centimeter that is illuminated with light of wavelength 565 nanometers. Make sure you convert everything to meters. That's what is given. Notice things are changed to meters. That is the equation. That is the equation for m equals 2. See very little difference, of course. And here we go. Now we want to plug in. That's the values for m equals 1. To find theta, 61.5, m equals 1, and m equals 2. Therefore, 1 is the highest order number that can be observed. Number 5, a diffraction grating is calibrated by using 546.1 nanometer line of mercury vapor. The first order maximum is found to be 21.2 degrees. Calculate the number of lines per centimeter on this grating. So same equation, we're simply going to isolate a different variable in the equation. That's what's given. And we want to find lines per centimeter. All right, so we want to find D. So we have the equation set up, we plug in, and we find D. 151 times 10 to the negative 4 centimeters, with the lines per centimeter of 6.63 times 10 to the third lines per centimeter. That is 6,630 lines per centimeter. Figure 20, each of two distant point sources produce a diffraction pattern. Diffraction and instrument resolution. The ability of an optical system, such as a microscope or a telescope, to distinguish between closely spaced objects is limited by the wave nature of light. To understand this limitation, consider Figure 20, which shows two light sources far from a narrow slit. The sources can be taken by 2 point sources that are not coherent. For example, they could be two distant stars that appear close to each other in the night sky. If no diffraction occurred, you would observe two distinct bright spots or images on the screen at the far right. However, Because of diffraction, each source is shown to have a bright central region flanked by weaker bright and dark rings. Figure 21, 2-point sources are barely resolved if the central maxima of their diffraction patterns do not overlap. What is observed on the screen is the resultant from the superposition of two diffraction patterns, one from each source. Resolution depends on wavelength and aperture width. If the two sources are separated so that their central maxima do not overlap, as in figure 21, their images can just be distinguished and are said to be barely resolved. To achieve high resolution or resolving power, the angle between the resolved objects theta should be as small as possible, as shown in figure 20. Resolving power, the ability of an optical instrument to form separate images of two objects that are close together. Look back at figures 21 and 20 and see if what is written here is understood there. The shorter the wavelength of the incoming light, or the wider the opening or aperture through which the light passes, the smaller angle of resolution theta will be, and the greater the resolving power will be. For visible light telescopes, the aperture width d is approximately equal to the diameter of the mirror or lens. The equation to determine the limiting angle of resolution in radians for an optical instrument with a circular aperture is as follows. Theta equals 1.22 lambda over d. The constant 1.22 comes from the derivation of the equation for circular apertures and is absent for long slits. Note that 1 radian equals 180 over p degrees, as discussed in the Appendix J feature, Angular Kinematics. The equation indicates that for light with a short wavelength, such as an X-ray, a small aperture is sufficient for high resolution. On the other hand, if the wavelength of the light is long, as in the case of a radio wave, the aperture must be large in order to resolve distant objects. This is one reason why radio telescopes have large dish-like antennas. Yet even with their large sizes, radio telescopes cannot resolve sources as easily as visible light telescopes resolve visible light sources. At the shortest radio wavelength of 1 millimeter, the largest single antenna for a radio telescope, the 305-meter dish at Arecibo, Puerto Rico, has a resolution angle of 4 times 10 to the negative 6th radians. The same resolution angle can be obtained from the longest visible light waves, 700 nanometers, by an optical telescope with a 21 centimeter mirror. To compensate for the poor resolution of radio waves, one can combine several radio telescopes so that they can function like a much larger telescope. Figure 22, the 27 antennas at the Very Large Array in New Mexico are used together to provide improved resolution for observing distant radio sources. The antennas can be arranged to have the resolving power of a 36-kilometer wide radio telescope. Absolutely fascinating. As example of this is shown in figure 22, if the radio antennas are arranged in a line and computers are used to process the signals that each antenna receives, the resolution of the radio images is the same as it would be if the radio telescopes had a diameter of several kilometers. It should be noted that the resolving power for optical telescopes on Earth is limited by the constant moving layers of air in the atmosphere, which blur the light from objects in space. The, the images from the Hubble Space Telescope are of superior quality largely because the telescopes operate in the vacuum of space. Under these conditions, the actual resolving power of the telescopes is close to the telescope's theoretical resolving power. Point out that the equation for resolving power is known as Rayleigh's criterion. This equation gives the angle theta in radians. 1 rad equals 180 over p degrees. For example, for light with a wavelength of 500 nanometers, a lens that is 0.1 meter in diameter has a limiting angle of 6.1 times 10 to the negative 6 radians, or 3.5 times 10 to the negative 4 degrees. This may seem like a very small angle, but for viewing the surface of Mars, nearly 75 times 10 to the 6 kilometers away, it corresponds to a distance of about 460 kilometers. This means a telescope with such a lens would show two mountains separated by a distance of 460 kilometers as one blurred mountain. Fascinating. Now let's begin the section review. Light passes through a diffraction grating with 3,550 lines per centimeter and forms a first order maximum at an angle of 12.07 degrees. What is the wavelength of the light? All right, so let's write down what we have and make sure we convert it to meters. In other words, lines per meter, add 2 zeros. And there we have lines per meter. We have m equals 1. And we have the theta, which is 12.07. There's the equation for lambda. And we'll calculate lambda by plugging in the values. And we get 5.89 times 10 to the negative 7th meters. We'll put that down to the left, and we'll do B. And what angle is the second maximum up here? Well, we're going to be able to put down the lambda. We have m equals 2. And we simply plug in the values. And we bring the lines per meter forward, and we get 24.7 degrees. Number 2, describe the change in width of the central maximum of the single slit diffraction pattern as the width of the slit is made smaller. The width of the central maximum increases as the width of the slit decreases. Which object would produce the most distinct diffraction pattern? An apple, a pencil lead, or a human hair? Explain your answer. A human hair, its size is closest to the size of the wavelength of visible light. Would orange light or blue light produce a wider diffraction pattern? Explain why. Orange light. Longer wavelengths are diffracted more. Number 5, critical thinking. A point source of light is inside a container that is opaque except for a single hole. Discuss what happens to the image of the point source projected onto a screen as the hole width is reduced. The image of the point source casts a sharp shadow when the hole is much wider than the light's wavelength. As the hole narrows, the light waves bend around the hole's edges, causing the image to widen. Light waves from the hole destructively interfere, producing a regular pattern of dark fringes on either side of the bright centrofringe. Would it be easier to resolve nearby objects if you detected them using ultraviolet radiation rather than visible light? Explain. Yes, ultraviolet light has a shorter wavelength than visible light, and resolving power is greater for short wavelengths. All right, let's start section 3. Lasers. Describe the properties of lasers. Explain how laser light has particular advantages in certain applications. Lasers and coherence. At this point, you are familiar with electromagnetic radiation that is produced by glowing or incandescent light sources. Did you know the light from an ordinary electric lamp undergoes about 100 million or 10 to the 8th random changes every second? This includes light from light bulbs, candle flames, or the sun. You may have seen another form of light that is very different from the light produced by incandescent sources. Waves from an incoherent light source left have changing phase relationships, while waves from a coherent light source right have constant phase relationships. The light produced by a laser has unique properties that make it very useful for many applications. Laser, a device that produces coherent light at a single wavelength. To understand how laser light is different from conventional light, consider the light produced by an incandescent light bulb as shown in figure 23. When electric charges move through the filament, electromagnetic rays are emitted in the form of visible light. In a typical light bulb, these are variations in the structure of the filament and in the way charges move through it. As a result, electromagnetic waves are emitted at different times from different parts of the filament. These waves have different intensities and move in different directions. The light also covers a wide range of the electromagnetic spectrum because it includes light of different wavelengths. Because so many different wavelengths exist, and because the light is changing almost constantly, the light produced is incoherent. That is, the component waves do not maintain a constant phase difference at all times. The wave fronts of incoherent light are like the wave fronts that result when rain falls on the surface of a pond. No two wave fronts are caused by the same event, and they therefore do not produce a stable interference pattern. Lasers, on the other hand, typically produce a narrow beam of coherent light. The waves emitted by a laser are in phase, and they do not shift relative to each other as time progresses. The word laser is an acronym, a word made from the first letter of several words that stands for light amplification by stimulated emission of radiation. Because all the waves are in phase, they interfere constructively at all points. The individual waves effectively behave like a single wave with a very large amplitude. In addition, the light produced by a laser is monochromatic, so all the waves have exactly the same wavelength. As a result of these properties, the intensity or brightness of laser light can be made much greater than that of incoherent light. For light, intensity is a measure of the energy transferred per unit time over a given area. Lasers transform energy into coherent light. A laser is a device that converts light, electrical energy, or chemical energy into coherent light. There are a variety of different types of lasers, but they all have some common features. They all use a substance called the active medium in which energy is added to produce coherent light. The active medium can be a solid, liquid, or gas. Atoms or molecules with added energy. A. Atoms or molecules in the active medium of a laser absorb energy from an external source. B. When a spontaneously emitted light wave interacts with an atom, it may cause the atom to emit an identical light wave. This is all figure 24. When an incoherent light source left have changing phase relationships, while waves from a coherent light source right have constant phase relationships. Here you're putting it all together. Figure 24. Please study it carefully and compare A, B, and C directly. The composition of the active medium determines the wavelength of the light produced by the laser. The basic operation of a laser is shown in figure 24. When high energy light or electrical or chemical energy is added to the active medium, as in figure 24a, the atoms in the active medium absorb some of the energy. You will learn that atoms exist at different energy states in the chapter Atomic Physics. Go back and look at figure 24 and see if it makes sense. When energy is added to an atom that is at lower energy state, the atom can be excited to a higher energy state. These excited atoms then release their excess energy in the form of electromagnetic radiation. When they return to their original lower energy states, when light of a certain wavelength is applied to excited atoms, the atoms can be induced to release light waves that have the same properties. After one atom spontaneously releases its energy in the form of a light wave, this initial wave can cause other energized atoms to release their excess energy as light waves with the same wavelength, phase, and direction as the initial wave, as shown in figure 24b. This process is called stimulated emission. Stimulated emission. Most of the light produced by stimulated emission escapes out of the sides of a glass tube. However, some of the light moves along the length of the tube, producing more stimulated emission as it goes. Mirrors on the ends of the material return these coherent light waves into the active medium, where they stimulate the emission of more coherent light waves, as shown in figure 24c. As the light passes back and forth through the active medium, it becomes more and more intense. One of the mirrors is slightly transparent, which allows the intense coherent light to be emitted by the laser. Again, figure 24 seems to be very pivotal. Applications of lasers. There are a wide variety of laser types with wavelengths ranging from the far infrared to the X-ray region of the spectrum. Scientists have also created masers, devices similar to lasers but operate in the microwave region of the spectrum. Lasers are used in many ways, from common household uses to a wide variety of industrial uses and very specialized medical applications, especially dermatology. Lasers are used to measure distances with great precision. Of the properties of laser light, the one that is most evident is that it emerges from the laser as a narrow beam. Unlike the light from a light bulb or even the light from a focus that is focused by a parabolic reflector, the light from a laser undergoes very little spreading with distance. One reason is that all the light waves emitted by the laser have the same direction. Let's continue at the bottom. As a result, a laser can be used to measure large distances because it can be pointed at distant reflectors and the reflected light can be detected. Let's read the misconception alert. Students may think that fluorescence and phosphorescence are related to the way lasers work. Make sure they realize that in fluorescent lamps, any atoms that become excited by absorbing energy immediately lose the energy by emitting light. In phosphorescence paint, the excited atoms are able to remain at a higher level of energy for a longer period of time, but they emit light spontaneously. In lasers, most of the atoms remain in the excited state until something triggers the excited atoms to emit light. You're going to want to read that again at your leisure. Figure 25, a laser beam is fired at reflectors on the moon, which is more than 380,000 kilometers away. Fascinating. Compound discs, why it matters. An interesting application of the laser is the compact disc player. In the CD player, light from a laser is directed through a series of optics toward a compound disc on which the music or data have been digitally recorded. The CD player reads the data in the way the laser light is reflected from the compact disc. In digital recordings, a sound signal is sampled at regular intervals of time. Each sampling is converted to an electrical signal, which in turn is converted into a series of binary numbers. Binary numbers consists only of zeros and ones. The binary numbers are coded to contain information about the signal, including the frequencies and harmonics that are present, the volume for the left and right channels, and the speed of the motor that rotates the disc. This process is called analog to digital, or A to D conversion. These binary digital data in a CD are stored as a series of pits and smooth areas called lands on the surface of the disc. The series of pits and lands is recorded starting at the center of the disc and spiraling outward along tracks in the CD. These tracks are just 500 nanometers wide and spaced 1600 nanometers apart. If you could stretch the data track of a CD out, it would be almost 5 kilometers long. When a CD is played, the laser light is reflected off this series of pits and lands into a detector. In fact, the depth of the pit is chosen so that destructive interference occurs when the laser transitions from a pit to a land or from a land to a pit. It's critical that you look at the illustrations and go back and forth and continue to look at the illustrations from the past slides. I picked out the illustrations for their comprehensive nature. The detector records the changes in light reflection between the pits and lands as 1 and smooth areas as zeros. Binary data that are then converted back to the analog signal you hear as music. Again, study the diagrams. This step is called digital to analog, D to A, conversion, and the analog signal can then be amplified to the speaker system. A CD read-only memory, CD-ROM, drive on your computer works in much the same way. Data from a computer are already in a digital format, so no A to D or D to A conversion is needed. You may wonder how a CD recordable CDR disc is different. These disks don't have any pits and lands at all. Instead, they have a layer of light sensitive dye sandwiched between a smooth reflective metal, usually aluminum, and clear plastic. So that's the difference. As they say, when the plot's about to thicken, the plot's about to thicken. A CDR drive has an additional laser, about 10 times more powerful than a CD reading laser, that writes the digital data along the tracks of the CDR disk. When the writing laser shines on the light-sensitive dye, the dye turns dark and creates non-reflecting areas along the track. This process creates the digital pattern that behaves like the pits and lands, which a standard CD player can read. A digital versatile disc DVD player operates on the same principle. In 1972, when I first read about DVDs in a trade journal, it said specifically that DVD didn't stand for anything. So curious that they have it standing for something now, but I don't know if what I read was true. CDs, CD-ROMs, CDRs, and DVDs all fall into a class of digital media called optical storage devices. The laser typically used for a CD player has a wavelength of 780 nanometers. Light in the near infrared region. A DVD player laser has a wavelength of 650 nanometers, visible as red light. Both of these lasers are diode lasers. These lasers are semiconductor devices that produce low intensity, coherent light when they carry current. Here is CD, DVD, HD, DVD, and a Blu-ray. However, the laser in a DVD player has a shorter wavelength than the laser in a CD player. This shorter wavelength allows the DVD player to read data that are spaced closer together than data on a CD. That's an old floppy disk, rather large floppy disk from the early 1980s. Amazing. Additionally, some DVDs contain two layers of data and may even be written on both sides. The lower layer of a two-layer DVD has a thinner coating of reflective material, usually gold, that allows some of the light to pass through it so that the upper level of the DVD can be read. As shown in Figure 25, astronomers direct laser light at particular points on the Moon surface to determine the Earth-Moon distance. A pulse of light is directed towards one of several 0.25 square meter reflectors that were placed on the Moon's surface by astronauts during the Apollo mission. By knowing the speed of light and measuring the time the light takes to travel to the Moon and back, scientists have measured the Earth-Moon distance to be about 3.84 times 10 to the fifth kilometers. Geologists use repeated measurements to record changes in the height of Earth's crust from geological processes. Lasers can be used for these measurements even when the height changes by only a few centimeters. Lasers have many applications in medicine. Lasers are also used for many medical procedures by making use of the fact that specific body tissue absorb different wavelengths of laser light. For example, lasers can be used to lighten or remove scars and certain types of birthmarks without affecting surrounding tissue. Did you know the principle behind reading the information stored on a compact disc is also the basis for reading of barcodes found on many products? When these products are scanned, laser light reflected from the bars and spaces of the barcode reproduces the binary codes that represent the product's inventory number. This information is transmitted to the store's computer system, which returns the product's name and price to the cash register. The scar tissue responds to the wavelength of light used in the laser, but other body tissues are protected. Many medical applications of lasers take advantage of the fact that water can be vaporized at high intensity infrared light produced by carbon dioxide lasers having a wavelength of 10 meters. Carbon dioxide lasers can cut through muscle tissue by heating and evaporating the water contained in the cells. One advantage of a laser is that the energy from the laser also coagulates blood in the same open blood vessels, thereby reducing blood loss and decreasing the risk of infection. A laser beam can also be trapped in a optical fiber endoscope, which can be inserted through an orifice and directed to internal body structures. As a result, surgeons can stop internal bleeding or remove tumors without performing massive surgery. Lasers can also be used to treat tissues that cannot be reached by conventional surgical methods. For example, some very specific wavelengths of lasers can pass through certain structures in the front of the eye, the cornea, and lens without damaging them. Therefore, lasers can be effective in treating lesions of the retina inside the eye. Lasers are used for other eye surgeries, including surgery to correct glaucoma, a condition in which the fluid pressure within the eye is too great. Left untreated, glaucoma can lead to damage of the optical nerve and eventual blindness. Focusing a laser at the clogged drainage port allows to open the hole to be burned in the tissue, which relieves the pressure. Lasers can also be used to correct nearsightedness by focusing the beam on a central portion of the cornea to cause it to become flatter. Section Review. Number 1. How does light from a laser differ from light whose waves all have the same wavelength but not coherence? Waves emitted by a laser do not shift relative to each other as time progresses. They are coherent and continuously in phase. Number 2. The process of stimulated emission involves producing a second wave that is identical to the first. Does this gaining of a second wave violate the principle of energy conservation? Explain your answer. No. The second light wave is obtained from the energy that is added to an atom in the active medium by an external energy source. Critical thinking. Fiber optic systems transmit light by means of internal reflection within thin strands of extremely pure glass. In these fiber optic systems, laser light is used instead of white light to transmit the signal. Apply your knowledge of refraction to explain why. Light Laser light is nearly monochromatic, so it does not spread out very much into different components with different wavelengths as it passes between the fiber and transmission of receiving equipment. That is, dispersion is nearly absent over short distances. It's one reason it's so good for surgeries as well. Section 1, interference. 3 points, key ideas. Light waves with the same wavelength and constant phase differences interfere with each other to produce light and dark interference patterns. In double slit interference, the position of a light fringe requires that the path difference between two interfering point sources be equal to a whole number of wavelengths. In double slit interference, the position of a dark fringe requires that the path difference between two interfering point sources be equal to an odd number of half wavelengths. Section 2, diffraction. Light waves form a diffraction pattern by passing around an obstacle or bending through a slit and interfering with each other. The position of a maximum in a pattern created by a diffraction grating depends on the separation of the slit in the grating, the order of maximum, and the wavelength of the light. Section 3, lasers. A laser is a device that transforms energy into a beam of coherent monochromatic light.